Good evening, ladies and gentlemen. We're Capstone Group 12, aka Iron Grip Robot, our soft robot team. Our advisor is Jian Lin. Our assistant advisor is Jungwin Su, and I'm Flynn McFeeling.
I'm Peter Eswine. I was the team leader.
I'm Victoria B.
Nami Reneza.
I'm Jordan Evans-Levitt.
So first we'll cover the concept generalization, then we will cover the gripper fabrication, and then the controls that control the gripper. We'll do some we'll cover some analysis that we did, and then finally end with our conclusion. So what is soft robotics? The definition would be a soft fluidic actuator that's made of elastomers embedded with a flexible material, aka what's kind of shown above to our left. So it's better than the traditional robotic arm or robotic arm hands that are on traditional robotic arms because it provides more flexibility and adaptability. It can grip unorthodox objects such as like a cactus or an object with more than 6 contact surfaces. It's also could be vital in such industries as packaging and manufacturing. It can help improve safety in the workplace. Also, we can expand it to medical applications and further, as shown up there.
So our objective was to create a soft robotic gripper that could safely transport fragile objects. This design just needed to be a starting point for Dr. Lin's research team. The main requirements were for it to be able to transport a tomato, a strawberry, and an egg safely without damaging it. And it had to be an easily reproducible design. And we also had to create the attachment to attach the gripper to the given robotic arm shown here.
Our total budget over one semester was $700. We reached that budget by having $66 left. The fabrication team spent most of the budget at $483, while the control team only spent $150. For comparison, Santa Clara University attempted a similar project. Their budget was $4,600 and they had 2 semesters to complete. That's 6 times our budget and twice the amount of time.
So, as Mia said, some of our constraints were that we had a budget of $700. And working with that amount of money was difficult, and we had to think out of the box to find solutions. We also had limited time. We had 4 weeks of balancing working class, and this was a key issue because we were all out of our element, and we had to teach ourselves how to use an Arduino, to wire a control board, how to use a 3D printer, and all this took a lot of time. So, as you might expect, there was some difficulty. This project was extremely hard. In my experience, I worked weekdays, weeknights, weekends, weekends. It was very, very difficult for me. Flynn has 2 jobs, and he had to be here working on this project as much as he could. Victoria drives here from Jefferson City every single day and gets started on this project early and stays late doing this project. Mia, from time to time, comes here at 5 a.m. to work on this project as much as possible. And Pete works harder than any of us. He and Flynn spent Thanksgiving working on this project, and he spent the whole Thanksgiving break working on this specifically. So, next is our QFD. For us, the most important aspect of the QFD was the gripper's lifting weight. We wanted to lift at least 1 pound, and as you'll see in the presentation, we did more than double that.
Our first design was modeled after a typical 4 actuator gripper. This involved 15 thin air channels. The mold was 3D printed and created the upper portion of the gripper. The lower portion was created by allowing a thin layer of silicone to cure. These 2 halves were then combined with silicone and sealing the air chambers. This prototype resulted in a gripper with very little bending and a large amount of ballooning in the actuators. We improved our first design by adding fabric to the lower portion of the gripper. This reduced stretching and resulted in bending. We now had enough curvature and therefore pressure to pick up items. The design still, however, needs improvements. The excess ballooning may cause difficulties in applications within smaller areas, and a standardized pneumatic tubing entrance needed to be created. We improved our mold. First, we addressed the excess ballooning. The air channel fins were then lessened from 15 to 6, and the volume was increased. This allowed for greater bending. The external walls were also thickened, which increased the pressure it could hold. The stem was added later, which served two purposes. One for an attachment to the robotic arm, and the other as a standardized insertion point for the pneumatic tube.
So after making improvements to the mold, we were able to 3D print a new one and make the new silicone gripper from it. And we found that it was able to resolve most of our main concerns, so it minimized the excess ballooning. It had the appropriate amount of curvature that was able to pick up the objects we needed it to. And the stem also helped to assist in sealing the pneumatic tubing and gave us a starting point for creating the attachment to the robotic arm. We also designed the attachment after we finalized this design. It basically just consists of two pieces. The top one kind of looks like top hat, but at the top of it, it allows room for us to attach the collar that attaches the gripper to the robotic arm, and it allows an entrance to the pneumatic tubing. And then this way it slides down and it bolts on to the bottom part, and it hides away the pneumatic tubing. So, to look for potential failure points, we conducted the FDA simulation, and to do this we had to use a special program called Igcsp. Not many FDA programs can deal with hyperelastic materials, so we had to obtain this, and we had a difficult time doing that. But once we obtained it, we actually had to learn the basics pretty quick, and we were able to construct a half section of one of our fingers. So we applied the pressure. We applied a minimal amount of pressure just to check the deflection, and when we checked the von Mises stresses, we realized that there was very minimal stresses. But the deflection showed that the finger would work as we intended. Even though our final design fulfilled all the requirements we needed, we also kind of started researching a more complex design that could offer us more benefits. This include individual finger actuation, which would allow us to use only two fingers if we need to pick up smaller objects. And if you were able to pull a vacuum, it would actually pull the fingers back and allow for a wider grip to grip larger objects. So we made a simple mold design, 3D printed that as well, and we used silicone to model one of the fingers, and we tested it to check for its deflection, and it worked as we expected. So we created 3 more fingers, and we're able to begin testing on the gripper, but we kind of ran out of time for this, so this is just a starting point that we hope to leave for Dr. Lynn's research team.
So, once the soft robotic gripper was designed, fabricated, the molds were made, and the gripper attachment was created, it was time to integrate all the components and attach the robotic gripper to the robotic arm we would use, as well as control the actual inflation that would cause the gripper to close and release objects. This was done by controlling the robotic arm with a PC running a graphic user interface that was downloaded from the manufacturer of the robotic arm's manufacturer. It's a Dorna robotic arm. This allowed us to directly control the movement of the robotic arm, as well as create Python and JSON code to directly create set movement paths that would be repeatable and set. Then the robotic gripper is attached to the robotic arm. As far as the controls of inflation and deflation, a signal is sent to the Arduino, which is the processing unit of our fluidic control board. This signal is close the gripper or open the gripper. The signal is actually a set point of pressure that we desire. The Arduino then sends a pulse width modulation to a MOSFET, which acts as a switch, and sends electrical pulses to solenoid valves mounted on a manifold, which is being supplied with constant pressure. Based on the duty cycle of the pulse width modulation, the valves open and close. When the valves open, pressure and airflow flows into the gripper, causing it to inflate and close around objects. When the valves open, air is allowed to flow out. By adjusting the duty cycle and how quickly the valves open and close, we can adjust and maintain the pressure within the gripper. Then a pressure sensor is used to constantly read the pressure within the gripper, and that sensor sends the information back to the Arduino, where the difference between the desired pressure and the actual pressure is calculated, and a PID controller then adjusts the duty cycle, the pulse width modulation, and adjusts it and able to reach the desired pressure that we want. So this is the fluidic control board that we made. It was a pretty challenging process since none of us had any background in electronics. The first component is quick connects that allows to quickly and efficiently attach soft robotic grippers. The second component is the power plug, where our 24-volt DC power supply is connected. It's not pictured here, but that's where it plugs in, which supplies power to the entire board. The third component is the on-off switch for the entire board, and we also have a power on-off switch that directly controls the power of the pump. Fourth component are power regulators, which are buck converters. They take the 24 volts from the power supply and drop them down to 5 volts, which is done on the left, which supplies power to the entire board. The one on the right steps 24 volts down to 12 volts and runs the miniature diaphragm pump. The fifth component is the pressure sensor that I mentioned. The sixth component is the MOSFET, which sends the electrical pulses to the solenoid valve, which is featured in 7, mounted to the manifold. 8 is the control switch. Currently, our control right now only uses one switch to send close or open signal, but we have included more to hopefully support future improvements, specifically with individual actuation. Number 9 is the Arduino 2560, and number 10 is the miniature diaphragm pump. The program basically operates by taking a set amount of pressure that we desire and having the board try to reach and maintain that. This is accomplished by using the pressure sensor, which takes basically a 5-volt source and breaks it into 1,024 individual discrete points and sends that amount of voltage to the Arduino, which is interpreted. 5 volts divided by 1,024 is about 4.8 millivolts, which correlates to about 0.122 psi. So that's kind of the steps of pressure that we have available to us. The manufacturer of the pressure sensor provided a transfer function to correlate the voltage read by the Arduino into actual PSI, which is there. So for example, a set point of 130 would correlate to about 3.369 PSI. Then, as I mentioned before, the PID controller is used to adjust the pulse width modulation duty cycle based on the feedback from the pressure sensor. So this is a closed loop system. To determine the actual PSI needed to grip the soft robotic gripper, we found that pressures below 2.758 PSI really only caused the gripper to oscillate a little bit. It would partially fill up, but it didn't cause any significant actuation. Pressures above 2.758 actually caused degrees of deflection. We went incrementally from that point and moved all the way up to about 3.369 PSI, which provided a good amount of gripping pressure, full actuation of the fingers, and also did not cause overpressurization that would cause plastic deformation and damage the gripper. We also tested the grip strength and lifting capacity of our gripper. We found with the 3.369 PSI, we had a lifting capacity of about 10.2 ounces and a grip strength of about 6 ounces. We accomplished this by taking a ball, hooking it to a basket, and loading weights into it until the gripper dropped it. We also had a second gripper that had a defect in one of the actuators, so we decided to overpressurize it and see what was possible. By overpressurizing the gripper, it caused extreme plastic deformation. However, it did show that the lifting capacity could theoretically be increased to about 2 pounds, 1.9 ounces, and the grip strength increased to 5 ounces. We don't recommend this because it destroys your gripper, but using the 3.369 PSI set point, and the fact that the heaviest item that we had to lift was only 6.1 ounces, this fell within our range of acceptability. And here's a demonstration of our finished project. The robotic arm, as I mentioned before, is being controlled by the computer using the Dorna graphic user interface. This is a set program that moves to a specific point, pauses while the gripper inflates, and then moves over to its end location and pauses while the gripper deflates, softly placing the object into the box, in this case a strawberry. The next object shown should be our tomato. As I mentioned before, the graphic user interface provided to us by Dorna allows us to create multiple different kinds of code. So this specific one is about the same path that the strawberry used, but it will omit the little wave there at the apex. And we should be picking up an egg next. And this was the one that we were most proud of and most worried about because we didn't want to drop the egg. And I'm pretty proud to say that after, what do you guys think, probably 6 or 7 runs, if not more, we never dropped the egg once, and it was completely undamaged. Touchdown. And then we hooked my phone up to the robotic arm.
I wasn't there.
What is it called? So in conclusion, the objectives that we met were we provide a gentle grip, so even the most sensitive fruit, which would be the strawberry, showed no sign of physical deformation or bruising. So it provided what we need is to secure even like fragile objects. And the next, we created a semi-autonomous robot arm. So it could move from starting point to point A to point B and back to original point without constant input. And then third, we integrated both concepts and created what you saw before in the video. And we could eventually create to a cyclic function, so we could move multiple objects over a duration of time. And next, we proved that we can lift even the heaviest object, which was the tomato at 6 ounces, so that gives us room to go further and get heavier objects or produce. And then for future recommendations, we recommend using stronger elastics. We had issues when we tested the robotic, soft robotic grippers, where after maybe a day of use or 2 days of use, they start not yielding the same results and started getting deformation slowly. Next, we wanted to increase the amount of overpressurization, which once you overpressurize it once, it'll cause a permanent deformation. And then next, pursue further research in the individual actuators, add a stronger pump to inflate it faster, integrate a VR system, and then integrate machine learning. This is our citations. Any questions? Yes.
Several things that I noticed. The first was that the fingers, as it flexed, were flexing asymmetrically.
Yes, they were.
And it strikes me that must be a quality control thing in terms of, either the internal dimensions or the thickness of the materials that are being used or something that's making one side more flexible than the other side with the same pressure. And I was just wondering if, when they finally got down to wherever they were going to go, if all of the fingers were contributing equally to the lifting, and whether you had tested the pressures of the individual fingers in the way.
We did not test the gripping pressure of each individual finger. They were all contributing because they were all making contact, and there was actually space in between each finger. So they were all contributing. Unfortunately, I do not know if they were all contributing equally. As far as them flexing individually, that is quality control. That could be variations in the walls, that could be, you got the mold variations, there could be some kind of difference in the air channels. Those are all, and that's one of the most challenging things that I think we had to face, was trying to go for the consistency.
The second thing that I noticed was that the goals were all volumetric, picking up things with volume, like a tomato and a strawberry and an egg. But the preview where you were showing the other groups trying to pick up a DVD off the tabletop. Made me wonder if you had given any thought to the engineering of the tips of your fingers to grasp things that were not going to be up in the main volume of the grip, but rather out on the fingertip.
We actually looked into that. We were in process of designing a mold that would incorporate fingertips that were a lot smaller that could pick up items. However, we kind of ran out of time, and we wanted to have a completely different option with the single finger inflation, so we decided to move forward. But that is the option to consider.
Also your first question, we had more time, we were install pressure sensors, which could help us get a better idea of how much force each fingertip is giving.
I think you're on the right track with the individual finger controls, because that would let you equalize every finger motion, by calibrating each finger.
Yeah.
The last thing, just kind of aside, was I really wanted to see a demo here of the tomato with max overpressure.
I know we were kicking ourselves earlier about not having to crush a beer can or something. Yeah.
So I like what you guys did with 3D printing, not just relying on that for your actual thing, but going into using it as the structure for your mold. I think it's a good application, especially for what, you guys did a couple of quick change things, which I think is pretty good. But getting back to the actual part itself, where did you guys start with the design? How did you conceptualize what that gripper should look like? What kinds of design considerations did you make in terms of the geometry that went into that?
As far as the geometries, we did do research when we first were tasked with this project. I don't think any of us were very familiar with what soft robotics were, so we did a little YouTubing and watched videos and to actually see what soft robotics was all about. And based off of things we saw on the internet, as well as we looked at a website called Soft Robotics and Soft Robotic Toolkit, and their reviews somewhat similar.
Also, our first experience was one of our advisors, one of their TAs, brought us into the lab and demonstrated the whole process from A to Z, to kind of how we set it up.
Did you make fingers or design the fingers?
Do we design? We designed a mold that was used to make silver fingers.
Yes, we designed the inner geometry, the air channels, the fins, as we call them, that actually inflate the cost of it.
So where it is made, the fingers?
Where the fingers, so the 3D, the mold is 3D printed, and then we mix silicone and pour it into the mold, and then we demold it after the silicone is cured. And depending which one we're looking at, the forefinger actuator has two parts, the top and the bottom. The bottom was just a fabric that was siliconed over. The individual fingers had an actual insert as well as, I said, tubs.
Any other question?
Anything else?
Gotta be one more.
You want one more? Okay, PID, did you have to tweak the PID or did you have to program the PID?
That was a rough one.
Yeah,
So,
please.
Did you have to use all three or were you able to?
we primarily used the P, we used the D a little bit, and then we barely used the I. In fact, there were times when we just turned it off, and it was so close, so we put a little in there, and it helped a little bit, but one of the problems that we faced, and it was probably the biggest problem with the PID controller, was when the valve closes, the pressure builds up behind the manifold, and then when it opens again, there's a big pressure burst, which causes the PID to overreact, and that was a big challenge. Through just a lot of playing around with it and tweaking, I tried adding longer tubing to try and put some kind of air cushion in between it and the pressure sensor. I shoved a piece of cotton in, hoping to put some kind of screen to just break that initial pressure burst. It ended up working, but I know I could easily spend at least another month just tuning that PID controller.
We're also thinking of incorporating filter theory and filtering out all the
Yeah, that'd be a really good idea.
or kind of errors.
Or if you had some kind of a reservoir or whatever. But yeah, I've been down the PID with
Yeah.
like heat controls before. It's a lot of fun.
Yeah.
I wanted to draw a point my hair.
Okay, thank you.